Hi students, welcome to my channel. Today we are going to start talking about the rocket engine, and this is lecture 78 in our aerospace engineering course. I'm Dr. Ranjan Ganguly. Now until now we have looked at various different types of propulsion. For example, we looked at the propeller, we looked at the jet engine and the ramjet. And in all these cases, these particular devices require air to generate propulsive thrust. So if you go back and look at the various equations, the various figures we have created, you will see that air was always an important part of this whole system. And we always had the air coming into the engine or into the propeller at some velocity v infinity. Now, of course, if you want to leave Earth, you want to go to space, you want to do interplanetary travel and so on, you do not have access to air anymore, and therefore you need to develop some kind of vehicle which can function without air. And this is something which the rocket engine does. The rocket engine essentially solves this problem by carrying both the fuel and the oxidizer. So when we are in the atmosphere, we can think of oxygen as being the atmosphere. So that's coming from outside. You don't need to carry it, and you only need to carry the fuel. And so rocket engines essentially do not need atmosphere, so the design of rocket engines is different and therefore they do not have any access to oxygen. So let's look at a typical schematic or diagram of the rocket engine. So what you have here is that you carry both the oxidizer and the fuel in these tanks here. So these are the two tanks here in many situations. Now what's going to happen is that this oxidizer and fuel mixture is going to form here, and then it's going to be combusted in the combustion chamber. In the combustion chamber you are going to have a temperature T0 and a pressure P0. Now remember, this particular mixture is coming in very slowly at almost negligible speed. So at this point the velocity is 0. So T0 is somewhat like a total temperature. Now, of course, there is going to be an acceleration here. This is a nozzle which is going to speed up the airflow to supersonic levels and so on. And therefore, you are going to have a very high exit velocity V subscript E, which is there at the end of the nozzle. Also, some more things to remember. The throat is here, and at that point, the cross section is A star, and the cross section is AE at the exit, and typically at the throat the Mach number is going to be 1. So that's the sonic condition. So now we are going to derive the equation for thrust for the rocket. Fortunately, we can use the equation for the turbojet which we have from before, but we have to keep some things in mind. We have to keep in mind that, for example, m dot air is going to be 0 because there is no air coming in into this system, and also the m dot air plus m dot fuel term, that's going to become the m dot oxidizer plus m dot fuel term. So with those changes we can essentially use the turbojet equation for the rocket engine also. So how do we do that? We start with the thrust equation for the jet, and we set m dot air equal to 0, so this term immediately goes. And then we also know that the m dot which is going out of the system, that is not m dot air plus m dot fuel, but it is now m dot fuel plus m dot oxidizer. So these two places are there, these two tanks, and from here the oxidizer and the fuel is coming, and these correspond to this particular m dot value. So if we make the substitution, the equation becomes much simpler. So we get the rocket engine thrust as T is m dot VE plus PE minus P infinity into AE. That's a small term here. Now, of course, like I mentioned, VE is very large, so the thrust of the rocket is going to be largely dependent on this exhaust velocity, which is going to be imparted to the rocket here. That's how the rocket generates most of its thrust. Now let us look at some of the equations we can get out of this particular system. So of course we can use the energy equation here. Do remember that we are in the high speed regime, and therefore we can use the enthalpy equation, that is H0 at this point is He plus VE square by 2 at this point. So essentially this equation is very critical here, and it's going to further resolve into this equation. If you remember that enthalpy H is Cp into T at any given point. So that's going to give you this particular equation. Now, if you are unfamiliar with this equation, you need to go back into the lecture and look at some of the basic equations we have derived for compressible flow and for isentropic flow and so on. Now we can make one more simplification in the thrust equation. We realize that when you are at this exit point of the engine, then PE is approximately equal to P infinity here. So this term is typically very small in comparison to the m dot VE term, and therefore we will say that thrust is equal to m dot VE. That's going to considerably simplify our life as far as the rocket engine thrust calculations are concerned. Now we look back at the equations we derived before, and we are going to invoke the isentropic conditions. So this was the energy equation between the 0 point and the exhaust point or the exit point. So from this equation we can immediately write the equation for VE square. So VE square would be 2Cp T0 minus Te, and I can write it in this form: 2Cp T0 1 minus Te by T0. Now, of course, we can assume isentropic flow, and then we can write Te by T0 is Pe by P0 to the power gamma minus 1 by gamma. And gamma, of course, remember, is the ratio of specific heats of the particular gas you are dealing with here. Then we get Cp is gamma R by gamma minus 1 here. So these two equations are essentially coming from isentropic flow. Again, if you are unfamiliar with them, you can go back and revise the lecture on isentropic flow, which we did long ago in this class. Now, after you make these two particular substitutions into the VE equation, you get VE in this form here. So I have substituted Cp is gamma R by gamma minus 1 here, and I have substituted Te by T0 as Pe by P0 to the power gamma minus 1 by gamma. And this whole thing is taken to the power half, that's the square root. So this is the equation for VE, and the main things you of course see here are the presence of T0, that's something very important, and also PE and P0 and the gamma being present here. So now we define a quantity which is very important as far as rocket engines are concerned, and they are actually used to quantify the thrust level in the rocket engines, and this is known as the specific impulse. So the specific impulse is given by ISP. This is T by W dot, where T is the thrust and W dot is the derivative of the weight, so that would be G0 into m dot, where we assume that this entire action and definition is taking place at the sea level. That's why we have G0 here. And now, of course, we remember the equation of thrust in its simple form was T is m dot VE. We substitute this into ISP, and so after that substitution we get this equation here, then we get this equation, the m dots cancel out, and we get ISP equal to VE by G0. So this equation also tells you that the specific impulse is going to directly depend on the exit velocity which is going to be obtained at the end of the rocket engine. So that's essentially the main thing which provides you with the thrust as far as rockets are concerned. So what we can now do is we can take a good look at the specific impulse formula, and to derive that what we do is take the ISP formula and simply substitute V of E here, and when we substitute V subscript E here, we get this formula which I have put in the yellow box. Now, of course, this formula tells you many things. One of them is that there is a direct proportionality of ISP with T0. That's one of the main parameters you are going to be able to control to increase or decrease your ISP. Now, typically you want ISP to be as high as possible because you want thrust to be as high as possible for a given expenditure of weight. So like I mentioned, T0 is very important. Again, recall T0 is the temperature in the combustion chamber. This is also known as the adiabatic flame temperature T0, and this is the temperature at which the fuel oxidizer mixture will typically burn. So this is not something you can do about much depending on the choice of the fuel and oxidizer you have made. These things are going to come here, they are going to burn, and that temperature at which they burn is going to be T0 here. So what you can do is select the oxidizer and fuel accordingly. Now, there are some specific combinations which you can use which are quite popular. For example, the most popular combinations are the first two of these, that is the kerosene oxygen combine that has a ISP of 240 second, then the hydrogen oxygen combine that has an ISP of 360 second, and also there is the hydrogen fluorine combine, but this is a somewhat volatile combine because fluorine tends to be very poisonous. It's also very corrosive, hard to store and so on. But this does have a very high specific impulse of 390. So of course you can see the hydrogen oxygen is also pretty good at 360, and in many cases when people have relatively lesser levels of technology, storage capacity and so on, they often resort to the kerosene oxygen mixture which has an ISP of 240. Now, the more important propellants, or I would say the one of the important propellants, are liquid propellants, and some of the liquid propellants are described here now. For example, you have cryogenic propellants, which of course means that they are at extremely low temperatures. So you would have H2 as fuel, that is hydrogen, and oxygen as the oxidizer. So this particular combination, it is obviously a very good combination. It's something which will yield to you pretty high specific impulse. This is also known as a bipropellant combination because you are essentially taking two chemicals and you are combining them. Of course, you have to keep them at very low temperatures. Now, there are also certain things known as monopropellants. For example, there is hydrazine N2H2. This is simple but has lower specific impulse. It's often used for some small rockets and also for the attitude control systems of many rockets where you need to only generate a small amount of thrust every now and then. There are also some things known as hypergolic propellants, and these are used for igniters. They ignite on contact. So for example, fluorine could be used here. It is poisonous, corrosive, but theoretically very good because of its good properties in terms of burning and so on. There are also certain mixtures such as mono, methyl hydrazine, MMH, and nitrogen tetroxide N2O2. Now, one interesting thing you will of course see in the study of these propellants for rockets and so on is that these are really things which are heavy in chemistry. And very often when people come to aerospace engineering, they think that it is only physics and math. But if you go into the propulsion side of the equations, particularly in the study of the fuels, then of course chemistry becomes very important because you are dealing primarily with chemicals. Now there are also solid propellants, and one of the reasons solid propellants are quite attractive is that liquid propellants need large tanks because these are of course liquids, and solid propellants have simpler carrying possibilities. Some of the solid propellants which could be used are given here. So there is one particular propellant which is a mix of various different chemicals. So here what you do is you take atomized aluminum powder 16%, this is the fuel, and the oxidizer is ammonium perchlorate, this is about 70%. Then you also put the iron oxide powder, that is about 0.7%, that's a catalyst. And then you use a rubber based binder which is polybutadiene acrylic acid acrylonitrile, and this is at 14%. Now the binder also burns like a fuel, so it is something which essentially binds all these other things together, and in a way you can imagine this to be somewhat like a sparkler which you burn at various festivals and at various Independence Day functions and so on. So what happens here is that this is like a completely solid product and it will burn once it is ignited. Now, solid propellants typically are quantified using a linear burning rate. So this is given by R is A P0 to the power n, and this is the time rate at which the burning surface of the propellant recedes normal to itself. So of course, as you are burning the propellant, it's going to diminish in its size, and so that receding rate is the burning rate. So here P0 is the combustion chamber pressure, and A and N in this equation here are experimentally determined coordinates or constants. These are typically zero point 0.4 to zero point 0.8 in value. Now, some of the advantages of solid propellants are that they are safer, simpler. There is no need for pumps. There is no need for complex, huge tanks to store those cryogenic materials and so on. And they can also be stored in rockets for decades. So, if you are devising some rockets, maybe you need to store them in some silos somewhere for use in some scenario which may or may not happen for a very long time, then you may want to use solid propellants there. Also, the volume is going to be typically less, but the disadvantage is that the specific impulse is less than liquid propellants, and cutting off burn once you have started it is difficult. So once you ignite a rocket, in this case a solid propellant rocket, it's simply going to go on burning. So that's something to keep in mind. So let's summarize this lecture here. So today we saw that in case you do not have air, what you do is you carry the oxidizer. So this is the simple and nice engineering solution to the problem. And in that case, what would happen is that you will have the fuel, you would have the oxidizer, you would burn them in the combustion chamber where you have a temperature T0 and a pressure P0. You would go through the throat, you would go to very high velocities and exit out here VE, and because VE tends to be very high for rockets, the thrust is going to be very high for rockets. So sometimes people try to actually create some kind of vehicle which is going to be powered by a rocket, and one of the reasons they do it is because they think the thrust is going to be very high, and that of course is a good part about the rocket. The efficiency is not so good, that we will probably discuss later. And we saw that the specific impulse is something which is used to quantify the thrust production of a rocket. So essentially it divides the thrust produced by W dot, or the time rate of change of the weight. And we also saw the specific impulse formula given by this equation here. And we saw this formula shows a lot of dependency on T0, which is the temperature in the combustion chamber. But this in turn is a product of the particular oxidizer fuel mixture you have selected. So of course the field of research here would also be in these particular fuel mixtures which you are choosing, because that's going to have an important impact on the thrust generated by the rocket and the specific fuel consumption. And that's really a problem in chemistry. So again, if you are somebody who likes chemistry, then the part of aerospace in which you will probably do well is the part involving propulsion and heat transfer and so on, and especially propulsion and the propellants. And therefore, maybe you can go for a master's degree or a PhD in that direction if you are somebody who likes chemistry and for some reason is stuck doing an aerospace engineering degree. So I will stop my lecture now. I think only a couple of lectures remain. In the next lecture, we are going to look at the multi-stage rockets, and we are going to look at the rocket equation, because as you know, most of the rockets when they take off, they are very large, but they keep shedding their components or their parts or their stages, and at the end of the day there is only a very small piece of the body typically which has the people in it, the passengers or the equipment, which goes off into space. So the rocket initially looks very large but keeps diminishing as it passes over through the atmosphere. So I'll end this lecture now, and I will see you in a video soon. Please subscribe to my channel if you have not, and spread it among your network.